project manager. This is Shafa, Ahmed. We're Acoustic Localization. And our faculty supervisor is Dr. Wage.
Well, we started off as a pad map, which is pond autonomous depth mapping, which was a vehicle that went on the surface of water to get a depth map. To have a depth map, we need a localization system, a local positioning system to tell us where the depth datums came from. Unfortunately, last semester we lost 2 team members, so we cut down our project to just acoustic localization. So the objective of acoustic localization is to use acoustic waves to determine the position of an object within a certain area using time-to-live arrival. So why use a local positioning system when we have a global positioning system available easily? Well, the typical accuracy of a global positioning system is plus or minus 15 meters, and it can get as low as plus or minus 1 meter per second. So we wanted to make a local positioning system that has an accuracy that's better than plus or minus 1 meter, or 3.28 feet. And so we decided to have an accuracy of our system to be 2.5 feet. So what are we really doing? Well, we have 2 speakers that act as the transmitters, and we're sending out a chirp signal. We need to distinguish one speaker from the other, which is why each speaker plays a different frequency. Now, if the speakers are transmitters, then we need a microphone to be a receiver. But why are we doing this? Well, simply to obtain a position of the object that's in the field. And a potential use of this project could be a data collection system, for instance, just the pad map itself. Now, what is the acoustic localization process? Well, there were certain issues that we had to overcome first. The first one being how to find the location of the object. And we use triangulation for that. Triangulation uses the distance between 2 known objects and the angle that the object in question forms with those known points. And then using the cosine rule, if we have the distance that the object has from the known points, we can calculate the angle. And if we have that angle, we can simply calculate using simple trigonometry the y value and the x value from one of the speakers set as reference. Once we have that issue overcame, we need to know how to calculate that distance from the speaker itself. Well, we use time-to-live arrival. Time-to-live arrival is the time it takes for the signal to be sent out from the receiver to be received at the receiver end. We know that the speed of sound in the air is 340 meters per second. If we can calculate the time that the signal takes to be received at the receiver, we can simply calculate the distance by multiplying the speed and the time. This shows a level 1 block diagram. We have 2 speakers that are connected to an amplifier and an MP3 player, which contains the chirp signal itself, and a computer at the receiver end, which has the microphone connected to it. When we begin, we define our grid. The grid is defined by the distance between the 2 speakers. Once we check that our system is on, we start recording. We initiate playing the chirp signal from the MP3 player, and we start recording at the same time. Once we're done covering the whole area that we're mapping, we stop the recording, and using MATLAB, a program in MATLAB, we determine the time, distance arrival, and eventually the distance. Once we have our distance, we can plot our coordinates on a graph.
Okay. And with that, there was a couple of other issues that we had to overcome. We had to find and account for all the delays in our system that was not the delay of the sound propagating through the air. And so we had 2 types of delays in our system. They were either random or they were constant. We had to determine whether those delays were random or constant. An example of a random delay, we had the MP3 player over on the side, and say if I press play and hey, yeah, I yelled start recording. We have 2 people, human error. It's not always going to be at the same time. So we have to account for that. We'll consider that random. Another example of a constant delay is the signal propagation through air, is what we're using to measure, and also through wires and through the system. Recording latency was another delay in our system that we had to account for. It's the time between the initiation of the recording and the actual recording. So what we did is we took our computer and our program, we connected the microphone jack to the headphone jack directly, And then we checked our program to see if there was any latency. And we did. And see, this graph shows that over 3,000 trials, right? What we did was we found that the latency was random for recording on the computer, right, using Windows. And we noticed that we had two Gaussian curves right here, that it was situated over like around 30 millisecond delay and 60 millisecond delay. And if we only had one, then we can account for just one and say most of the values would lie around here and say it would be off this percent of the time. Okay? And so we needed a method, because this is random, also to account for the playing and starting the recording, to account for all the system delays, whether constant or random. And to do this, we implemented a method called an initialization point. Okay? And so, initialization point, if you look at this is a plot of our received chirp, our recorded chirp in red, and this is our transmitted chirp in black. And see, what I did here was, part of this is random delays, part of it is constant delays, and part of it is I waited 1 second before I played and started recording. So I added this delays here. And so for the initialization point, you have to know the first point that you're measuring. And so for this point, in this blue box here, we assumed that it was a 0 for this test. And so we said, well, this should be at 0. All the other chirp sequence is off by this latency. And so what we do is we correct for it based upon this chirp here, and then we move all the other ones. So all the other chirps were actually at 0, and so now we measure it correctly. Okay? There are a couple of limitations to the initialization point, just to make that clear. The first thing is that you need to know the first location of the recording. That is the biggest limitation. A way to get around that, way we got around it is, say there's 2 speakers right there. That's how we did it. We just stand next to one speaker, and we've mapped the grid size. Say this was like 10 meters across. Then we say we started at 0, 10. So we start in front of one speaker, and that would be the initialization point. Next thing is that you have to have a large enough window in order to view the initialization point. If we look back here, right, the delay was inside this window here for the initialization point. But say if I waited like 10 seconds to start recording, like I got distracted, and I said, hey, start it, and I got distracted, and then I waited 10 seconds, then I started playing. You need a big enough window, or else this delay would be out on where the chirp sequence would be. And so by specifying a big enough window, you're able to view the first initialization point. And the next thing is that the measurements for the chirp sequence are error sensitive to the initialization point. You get the initialization point wrong by any little bit, then it's going to transfer over to the chirp signal. But it's at a constant, so you'll be able to see that. Okay, so we overcame the method for finding location, determining positions, and we found and accounted for delays in our system. And this is our level 2 block diagram. What we were trying to do was use 4 speakers in order to narrow down that accuracy, to get it more accurate. And but we originally had a bandpass filter, which we didn't get a chance to fully implement, and Shafa will discuss that later. But yeah, so we ended up using 2 speakers in first, and so we were able to still measure and take measurements up there. And also another thing was that we weren't originally trying to use just time delay of arrival. We were trying to use angle of arrival too, and combine them together to get better accuracy, which would use trilateration and triangulation for both of the methods. So updating the flowchart, now we need to determine the initialization point and specify the window before we even get started. And then now the program has to take into account the time delay of arrival and the distance based off the initialization point. And now testing. First thing first is how well can the program that we have in MATLAB deal with noise and taking care of noise. And as you can see right here, this graph right here is, I took 5 values, shifted them in known delays, right? Then added additive white Gaussian noise, then put it through our program, and with a signal to noise ratio between a negative 100 dB to about 100 dB. And then I ran that for about 30 trials. And as you can see right here, unless all the values were 100% correct, I didn't map a percentage correct as they were being 100% correct. So you see right here, after this threshold, they're 100% correct. And so after an average about 30 trials, we found out that that value tended to be around negative 27.6 dB signal to noise ratio. And then we just said, oh, let's give it a guard of 3 dB and called it negative 24.6. Another test that we did was measuring for accuracy. We did it with one speaker first just to measure time delay of arrival in just our system. We did it from 0 meters to 5 meters, a half a meter to a meter. And we did this for 100 trials, and we did it to measure accuracy up to plus or minus a quarter of a meter. And here's a sample value of 10 of the values. This is the average of the total. Around 0, it wasn't quite at the front of the speaker, so it measured like 0.8 centimeters from the after initialization with a standard deviation of 6.1 centimeters. For half a meter, it was 46. It should have been 50 with a standard deviation of 10. And at 1, it was at 94 and a standard deviation of 11. So it was pretty close near the values that it should have been by centimeters. Next thing we did was try the same thing again, going out long distance, see if there was other problems with that. Maybe something might come up if we're going out too far. We did that for every 2.5 feet. Couldn't find like a meter like tape to save my life, so I used feet measurement. And we measured accuracy up to 2.5 feet. And here's this is a graph of just to notice this. Just part of the plots is just 15 feet. We measured 16.9 feet on average with a standard deviation of 1.15 feet. Okay. Next thing we did, we want to test the initialization point and how well it worked, depending on if it's, do we need to be right next to the speaker or could I be at the back of the room to be initialized. So what we did was we took the initialization point, we started at 0, then we moved every 5 feet up to 50 feet away, and we initialized it differently at different points. And we did 11 trials for that. And as you can see in these red circles here, this is where the points should actually be. This is just one trial right here, the first trial. So we initialized it at 0, it's there, and then each point afterwards. But we took the average of all the trials for the 50-foot mark to see, because all of them had the 50-foot value. And the average was 51.1, and then the standard deviation of 2.59 feet. Another problem that we had was we were standing in the way of the mic for some of the tests, and we were like, why are these values just so off? And so Dr. Wade suggested that we test with an obstruction in the way. And so we did that. We kept the mic consistently at 20 feet, and then we placed myself on the human obstruction. And then I moved from the mic all the way back to the speakers in between it. And I did that every 2.5 feet away, and we did 10 trials for that. And as you can see right here on the graph, in this black circle, we're at 20 feet. Most of the values lie around that value. So, but as you can tell, like the average here was 17 feet, and different standard deviations. So it does matter where if you stand in front of this thing. That's what we were trying to find out. Movement line test. We were trying to see how well the system could actually track us and when we're moving out in the field. What we have here, we started right here. It's kind of changed on our graph, but we started right here and we moved up. I chose this graph in particular. You notice that it's not a straight line, but I chose this one in particular because we noticed one other factor that was messing up our values. This factor was when we started speeding up and moving really fast. It was starting to get dark outside, and then when we noticed that, oh, we need to get done before it gets too dark, we started speeding up, and then the values didn't plot. So you have to move at a certain speed consistently, or else it's not going to be able to track you for at least for now. We tried it again at a much slower rate, a triangle test. Here's the area that we kind of mapped out, but this is the tracking that we actually had from the system with 2. I mean, it's not perfect, but we got a triangle. So, next thing is a video of us testing.
issues. The first of them being the bandpass filters. Well, I was able to design the bandpass filters, but they worked fine with the signal generator, but when we used the sound signal as the input, somehow they weren't filtering out the sound at the cutoff frequency. And so we settled for using only 2 speakers to get the distance.
Another problem that almost drove me insane was when we were using the iPod as our sound source. The initialization port worked for a lot of different scenarios. Like I played it in Windows Media Player like 15 seconds afterwards, and then had it correct and played it in different media players. And then also like when we used the iPod, it corrected it accordingly, but for some reason it wasn't sending the same chirp that I put in that iPod. And so what happened was like each chirp was increasing, adding another additional delay per chirp. So every chirp, like the first chirp would have 1 delay, and then by the time you hit 30, you were like all the way out there. So and then that was messing up our values, and I couldn't know when we were doing our testing. Yeah, our lessons learned. Innovation reduces costs. We kept it really cheap by just, even with the initialization point, trying to figure out ways to use what we had to do what we wanted, right?
We also learned that time is the most important resource. We have to make use of our time and start early enough, and so that we finish early.
And the last one is make the most use out of your people network. We were able to get like those cones that you saw in the video. We were actually filming in the park. Like I actually worked there, and I actually just asked my boss, "Hey, can I work there?" So it was just making use of connections, and getting the speakers were free. I just borrowed them from a friend, and the only thing we really had to buy was the mic and the amp and the battery to power it up. Cost figures. This is about speaker wire costs like $30 because we got 30 meters, but we got high end, so when it about 16 gauge wire, and then the microphone extensions, and then the microphones and the audio amplifier. Everything else was done in MATLAB. And these were our hours spent. We said for this type of for this project, we spent this much. Obviously, we worked more last semester, but we also had to cut off. Like we said, we'd be generous by cutting off the work that actually didn't go to the acoustic localization, but went to PatMat. So we did this. An alternative design is using ultrasonic sound. We were in the park. We were driving. Some men like walked by with dogs, and we were driving them insane. They were just like looking up. So, and I never want to hear a chirp again. So I'm tired of listening to them. So using ultrasonic sound would probably be better. That's what we're going for. Acknowledgements. We want to acknowledge Dr. Wage, who's been a huge help for our project in terms of giving us advice and being on us and keeping us going. We really appreciate that. And also Dr. Nelson, too, for when Dr. Wage was away for about a month or so for filling in as our acting faculty supervisor. And you got up to date pretty fast, and we thank you for that. Any questions?